Hello, Royals. Lesson 6.6 on binomial powers. It seems a little bit out of place with our sequence and series. I'll try to convince you that there's some recursive definitions here, but it's actually going to be more useful sooner than your sequence and series work. In calculus, you'll have the choice to either factor expressions or expand them. And while factoring expressions is more efficient, it's nice to know that they can be expanded, and you'll have to expand it for at least one proof. So in the lesson, here was an example of a binomial power. This is a binomial inside the brackets here. It has two unlike terms, and it is raised to an exponent. So you have a binomial power. And this experiment here was just sort of to illustrate how tedious this is. It's kind of like a recursive definition, isn't it? To figure out x plus y to the exponent 5, I would need to know what x plus y to the exponent 4 is. To know what x plus y to the exponent 4 is, I would need to know what x plus y to the exponent 3 is. To know what x plus y to the exponent 3 is, I would need to know what x plus y to the exponent 2 is. Well, I kind of know that one. And the suggestion has been made in the past that this could have been sped up by saying, well, isn't this x plus y times x plus y just another one of those? I would just have to distribute through the three terms there. Now, the most important thing that we recognize, and this should be a review of a fact for us, is that exponents are not distributive through sums or differences. So x plus y to the exponent 5 is not x to the exponent 5 plus y to the exponent 5. Just try it with numbers to convince yourself that that doesn't work. You've illustrated this since grade 10. You should know this to be true. Okay, so what we want to do is try to find a sort of faster way of doing this. So what we do is we start to recognize these coefficients. There's a coefficient of 1 up here, of 1 and 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and 1, 5, 10, 10, 5, 1. And those coefficients come from Pascal's triangle. So let's construct Pascal's triangle together. The definition is written down on your lesson, so I won't write it down here, but we can sort of follow along. So Pascal's triangle is a recursive definition. It says that every row has one more elements than the previous row. Okay, that doesn't really help me to start. The first row has only one element, and the first element is 1. This means the second row is going to have 2 elements, and one of the base case definitions is that outside elements are always 1. Okay. This next row here is going to have 3 elements, so I have an inside element. And the recursive case of the definition here, these are all sort of like base cases. The recursive case says that any interior element is the sum of the previous adjacent terms in the previous row. So this element right here is going to be that term's value plus that term's value. Now you can define this recursively in advanced functions. You could, but you're going to need 2 subscripts to do it. It's not a function on one variable. You're basically saying that this row's element is elements from the previous row and previous positions. I'll try to get that down maybe once we have a way of labeling these rows and elements, but it's not that important for our course. So the next row, exterior elements are 1. Interior elements are the sum of the previous, adjacent elements in the previous row. So 1 plus 2, that's 3. 2 plus 1, that's 3. And you're going to notice that Pascal's triangle is symmetric, so you don't really need to create the whole thing, but you also can't really split this number in half, so you might as well construct the whole thing. It doesn't take twice as long. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. You've probably experimented with Pascal's triangle before, and if you plan on taking data management, you will work with it again. There are a number of interesting patterns here. These are the natural numbers. These are triangular numbers, I believe. There's the hockey stick pattern in sums. Look up a video on patterns in Pascal's triangle, just for curiosity's sake. It's not something you're going to need to communicate in this course. But okay, now we name things a little bit differently here than we do with a regular sequence or series. So that things line up nicely, we call this right here row 0. And we'll have another explanation for this, but notice if we do this, then each row can be numbered by its second element. This right here, where your second element is 2, is going to be row 2. This right here is going to be row 3. This right here is going to be row 4. Okay? Here's row 5. So asked to write row 5 of Pascal's triangle, I actually need 6 rows because I need row 1, row 2. As far as generalizing this, so there is a mathematical way of generating these numbers without generating all of the numbers before, but it is a topic for data management. If you look up the binomial theorem or Pascal's triangle, you might find some complicated calculations with permutations and combinations. I'm going to suggest that you not try to use those. It's not going to be useful for you in this course. You're not going to need to figure out the 17th row of Pascal's triangle in this course. That would be a tedious question to do in using this method because it's a recursive definition. I would need the 16th row, the 15th row, the 14th row, every other row all the way back. It's a lot of calculations. Yeah, so if you're really curious in those types of patterns, take data management. If you're also interested in exactly how this works, take data management. We're just observing that this works. So the way that we can use this is that if we are asked to expand x plus y to the x plus y to the exponent 5, then what we use is row 5 of Pascal's triangle. That becomes, let me just make sure I have enough space here. Those are the original coefficients on my terms. There's going to be 6 terms in this expansion. The first term is going to have an original coefficient of 1. The next term will have an original coefficient of 5. The next will have an original coefficient of 10. Then another 10, and then another 5, and then another 1. So you see how much space this takes expanding it out. Okay, each term is going to be a power of a product of the original coefficients from row n, row 5, with powers of these two bases. So I'm going to be multiplying these coefficients by powers of x and y. Different powers of x and y, of course. The exponent on x is going to begin at 5 and decrease by 1, 0, until I reach 0. The exponent on y is going to begin at 0 and increase by 1 until I reach n, or 5. So you're going to notice a couple of things here. There is a pattern in the coefficients. That pattern comes from Pascal's triangle. There's a pattern in these exponents. 5, 4, 3, 2, 1, 0. That's an arithmetic sequence with a first term of 5 and a common difference of -1. 0, 1, 2, 3, 4, 5. That's an arithmetic sequence with a first term of 0 and a common difference of 1. But what you're actually doing here, x to the exponent 5, x to the exponent 4, x to the exponent 3, that's a geometric sequence with a common ratio of the reciprocal of x. 1, y squared, y cubed, that's a geometric sequence with a common ratio of y. So there's a lot of sequences and series going on in this question. And then we usually tidy this up a little bit. So let's see, 1 times x to the exponent 5 is x to the exponent 5, and y to the exponent 0, as long as y isn't 0, is going to be 1. If you're using this tool to figure this out when y is equal to 0, you're using the wrong tool. If y is equal to 0, then you don't have a binomial. I'll have plus 5x to the exponent 4y plus 10x cubed y squared plus 10x squared y cubed plus 5x y to the exponent 4 plus y to the exponent 5. And it's not super fast, but it is faster than doing the full expansion as illustrated in the first case. The other pattern that I forgot to point out on the original exponents is that the original exponents, they always add up to 5. That's called the degree of the expression. Okay? Now, things change a little bit when you change the coefficients. Let's do some examples that aren't on the lesson. Let's expand and simplify. X minus 3 to the exponent. Yeah, let's do 6, I suppose. This is going to take up a lot of space. So I need row 6 of Pascal's triangle. Luckily, I already have row 5. Let me just sneak in row 6. Row 6, first element is going to be 1. The second element is going to be 6. That's about as far as I have memorized. The next elements, 15, 20, 15, 6, 1. So I don't think I'm going to try to fit this on one line. I think I'm just going to regret it. I'll split it up roughly in half. I'll have 4 terms on the first line and then the next 3 terms on the next line. So this is going to be 1 something something plus 6 something something plus 15 something something. It's tempting to try to fit the rest in, but I know I can't. Plus 20 something something. Go down here, plus 15 something something. I should be saying something else. Plus 6 something something else. Plus 1 something something else. These bases are going to be x and -3. Notice you need brackets to have a power on a base of -3. You didn't need brackets around the x here, but you kind of need the brackets for the multiplication anyways, so you might as well use them. X -3, x -3. I'm not sure. I kind of like doing things in this order. I think it gets sort of a muscle memory going, and I get really fast at writing x -3. X and whoops, not that accurate though. X and -3. So I like getting my coefficients out of the way, getting my bases out of the way. I feel like that's faster than doing 1x -3, 6x -3, 15x -3. You might disagree. Next thing I'm going to do is I'm going to do 6, 5, 4, 3, 2, 1, 0, and make sure that I end at 0. And do 0, 1, 2, 3, 4, 5, 6. Make sure that you start at 6, end at 0, start at 0, and end at 6. So if we were together and if I could show you a simulation here, we might have a better understanding of how this works. I'll just stress again, you do not need to understand how this works for this course this time through. But basically what you're looking at here is like a Plinko probability. Look up Plinko on The Price is Right, and you'll see it's like this right here is tracking how many different pathways. If I'm only allowed to go left or right down here, then there are 6 different ways that I can get here. So what I'm actually counting is all of the number of like terms that show up in these expansions. But there's going to be 15 of these terms altogether. There's going to be 20 of those terms altogether. It's fascinating how it works, and it's unfortunate that in our course we rarely have time to really look at how it works. Okay, so in this video and in the lesson, I sometimes refer to the original coefficients and the original exponents. Our exponents of 2 and 3 and 4 here on these bases in -3, they're going to disappear because I'm going to evaluate those powers. And my coefficients of 6 and 15 and 20, those are going to change because of these powers of -3 as well. I'll still see the exponent of 6 on x, which should make sense. If you imagine doing the first times 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 the first, you're going to have an x to the exponent 6. You're also going to have an x to the exponent 0 and a -3 to the exponent 6 there. There's the first term and there's the last term. It's all these inside terms that are harder to count. So here we go. Let's spend a little bit of time tidying up. And I'm going to take 2 steps through this. I'll see how you feel about maybe doing it in 1 step. 1 is 1. X to the exponent 6, x to the exponent 6. -3 to the exponent 0 is 1. There's a 6. X to the exponent 5 is x to the exponent 5. -3 to the exponent 1, that's -3. 15, that's 15. X to the exponent 4, just do that there. -3 squared, that's 9. 20, x cubed. -3 cubed, that's -27. Do you see the geometric sequence showing up here? And maybe the reason why I'm taking a step, I'm not doing 6 times -3 with my calculator here, is I think this actually will go faster if I don't pick up my calculator. I'll get better at multiplication if I practice without my calculator. And I also want to just make sure that I see the pattern here. Let's see, 15x squared, that's going to be 81. If I ever get lost in my powers, I can just multiply the previous power by 3. Plus 6x, that's going to be like here, for example. I don't know what -3 to the exponent 5 is. What's 81 times 3? It would be 243. Let me just check that. I don't want any mistakes on here. Yeah, 243. I'm lost. Oh, there we go. Plus 1, x to the exponent 0 is going to be 1. And then negative 3 to the exponent 6, 240. Well, let's see what we can do by hand. 243 multiplied by 3, 9, 12, 6, 7, 729, of course. Okay. So I like showing this intermediate step, and in our next example, you'll see that it's even more useful. This intermediate step tends to be better on more challenging questions. I suggest doing it. You're not going to be doing so many of these expansions that you need to skip a step. And it's just frustrating when none of your coefficients are correct. So on this last step, what I'm going to do is just multiply these coefficients together. 1 times 1 times x to the exponent 6, that's just x to the exponent 6. I wonder if I can fit all this on one line. Let's try it. 6 times negative 3, that's going to be negative 18x to the exponent 5. 15 times 9 is going to be 15 times 10. That's 150 minus 15. That's 140, 135. Positive times negative. 20 times 27 is going to be 10 times 27. That's 270 times 2, 400, 540. Oh, 15 times 81. I could do 10 times 81 is 810. And then half of that, because 5 times 81 would be 405. So 5, 1, 12, 1,215. Where did I go? Right, 15 times 81. Yeah, 12, 15. And I've got an x squared. I might be out of tricks here. I guess I could multiply by 3 and then multiply by 2. Or I have my calculator in my hand. 1458x plus 729. There we go. Now, can you imagine, in the past, if we had like x minus 3 squared and we accidentally wrote it as x squared plus 9, I mean, we missed one term, right? But we probably should still be losing a lot of marks because it's a very serious mistake. Can you imagine, though, if someone always thinks that x minus 3 to the exponent 6 is just x to the exponent 6 plus 729? This is going to cause serious problems in future courses. Okay. Some students really just like to hang on to distribution. They just distribute. And we have seen that almost no other operation other than multiplication and division is distributive across sums or differences in this course, or in mathematics. So patterns now. You can still see the pattern on the exponents and in the powers and factors of x. The pattern in these coefficients has been obfuscated. It's a big word that means made less visible or made hard to see on purpose, maybe. It's because it is a pattern that includes powers of 3. And I realize I've got a mistake here because I should be alternating, shouldn't I? Where does my negative go? Yeah, this right here should be negative. That's an odd exponent. Negative power. Should be going positive, negative, positive, negative, positive, negative. That pattern remains. But yeah, don't go looking for a pattern in 118, 135, 540, 12, 15. These values increase and then decrease, and they can be very complicated because it's also based on this pattern right here, this 1, 6, 15, 20, 15, 6, 1, which is also a difficult pattern to generalize. Okay. All right, last kind of example I want to do is find the first 3 terms or find the first 4 terms of. Let's find the first 4 terms of 2x cubed minus 3y squared to the exponent 8. So notice I'm kind of at a space on my screen here to have the Pascal's triangle show up and this. I also don't have a lot of room to do the 8th row of Pascal's triangle. But I also don't need the entirety of Pascal's triangle. If I'm asked for the first 4 terms, I only need the first 4 elements of Pascal's triangle. Also, when we say the first 4 terms, we probably mean if we had expanded this from left to right and left the 2x cubed out in front. There's no rule that really says that this has to be the first term and that has to be the last term. But most people understand that to be the case. Okay, so just to illustrate how it shouldn't take too long to generate the first four terms of the eighth row of Pascal's triangle. Let's just do it fresh. Here's 1, here's 1, 1, here's 1, 2, 1, 1, 3, 3, 1. And now I'm not going to do any more further to the right of that. I'll go 1, 4, 6, 4, 1, 5, 10, 10, 1, 6, 15, 20, 1, 7, 21, 35, 1, 8, 28, 56. And those are the numbers that I need just by adding. Once again, if you can get fast at adding without a calculator, this is not gonna be faster with a calculator, having to type in all of those additions. The notation as well. Students are a little bit awkward or feel a little bit awkward here. I'm fine with you writing equals here. I mean, assume that this is saying the first four terms of this expansion simplified equals this, and then just use an ellipses or a dot, dot, dot. It's going to be 1 bracket bracket plus 8 bracket bracket plus 28 bracket bracket plus 56 bracket bracket. And then there's some more terms, aren't there? Like 5 more terms that we're not too interested in. See, we want to make sure that students can expand these with higher exponents. I think on your homework sheet, you're going up to an exponent of 14, but we also are not interested in seeing 15 terms written out in your homework. So read your directions very, very carefully. If you see the first 4 terms, please do not get more than the first 4 terms. All right, this is going to be 2x cubed, 2x cubed, 2x cubed, 2x cubed. Notice I changed my pattern there. I just put in the first base because it was a little bit more complicated. Now I can put in my second base. I'm a little cramped for space here. I want to make sure I don't miss any negatives like I did in the last example. And then be careful with the pattern here. You won't have that same check of making sure that you finish at 0. So the exponent on the base of 2x cubed, the first power, is going to be 2x cubed to the exponent 8. That exponent is going to go down by 1, 7, 6, 5. This exponent will start at 0 and increase by 1. I suppose the check that you have is ensuring that your original exponents always have a sum of 8 there. And we're saying original exponents because in this example, our exponents will be changed by these exterior exponents, by the powers of powers. The numbers are a little bit bigger, so let's work carefully and check with a calculator. I mean, you want to practice by hand, but don't make a mistake on 2 to the exponent 8 just because you're trying to show off. Let's see. So I'm going to have 1. 2 to the exponent 8 is 256. That might be, maybe that's the only power of 8 that we need to calculate. Now, be careful here. This is 2 to the exponent 8. This is not 3 to the exponent 8. This is x cubed to the exponent 8. This is 8 groups of 8 factors of 2. And now this is 8 factors of x cubed. So it's 8 groups of 3 groups of x. That sounds like 24 groups of x. I suppose I should be able to use my grade 9 power laws of keeping my base and multiplying my exponents, but it works if you understand what it means as well. Non-zero base to the exponent 0 will give me a power of 1. Then I've got an 8. Do you see here how it might be a little bit confusing to try to do 8 times 2 to the exponent 7 times negative 3 to the exponent 1, and then remember the power of x and the power of y as well? So let's just expand this or evaluate this. So this is what I meant by maybe we only need to calculate 1 power of 2. If 2 to the exponent 8 is 256, 2 to the exponent 7 is half of 256, which is 128. Then we'll have x to the exponent 21. A negative 3 to the exponent 1 will be a negative 3. And that, I think, is supposed to be a y squared to the exponent 1 will be y squared. And again, I have run out of space. So let's go down another line. Here's a 28. 2 to the exponent 6, half of that, 64. X to the exponent 3 to the exponent 6, x to the exponent 18. Negative 3 squared, positive 9. and y squared squared, y to the exponent 4. Then you'll see a 56, 2 to the exponent 5, half of that, 32. X cubed to the exponent 5, that's 15 factors of x. Negative 3 to the exponent 3, negative 27. Y squared cubed, that's 3 groups of 2 groups of y. That sounds like 6 groups of y. Almost ran out of space again. Let's look at some patterns. 256, 128, 64, 32, geometric. 24, 21, 18, 15, that's arithmetic, but x to the exponent 24, x to the exponent 21, x to the exponent 28, that's geometric. 1, negative 3, 9, negative 27, that's geometric. That's an alternating sequence. That's why we'll see a sign change going from positives to negatives in our terms. Remind me to show you that this skill works actually for exponents of 0 and exponents of 1 and exponents of 2, but I don't think you'll want to use that. So what have we got left to do here? Really just some tidying up. We have a 1 times a 1 times a 256. That's going to give us, I'm going to leave a space, 256 x to the exponent 24. Then I've got 8 times 128 times negative 3. 8 times 128 times negative 3. Don't be a hero. Negative 30, 72. And I'll have x to the exponent 21 y squared. Then I'm going to have positive times positive times positive. 28 times 64 times 9. 16,128. X to the exponent 18. Y to the exponent 4. And not enough space. Positive, positive, negative, minus 56 times 32 times 27. 48,384. 15 factors of x, 6 factors of y. It would look a little nicer if it was all on one line, but we've got to give our writer a break here. Okay, it's pretty advanced stuff. And I mean, you could always ask a computer to do this for you too, but it's pretty cool how we can use some simple patterns to do this. Oh yeah, so x plus y to the exponent 0, use the 0th row of Pascal's triangle and write a 1. X plus y to the exponent 1, use the first row of Pascal's triangle. You're going to write 1, x to the exponent 1, y to the exponent 0, plus 1, x to the exponent 0, y to the exponent 1, to figure out that you get x plus y. But it's still cool, I suppose, that it works. And x plus y squared, which we worked all the way up to grade 10 to be able to figure out, is going to be 1x squared y to the 0, plus, because you have an xy plus an xy, there are 2 of those terms. This is where maybe we can start to develop an understanding of how you're counting all of the different ways of multiplying these different terms together. That's what those coefficients do. Plus 1x to the exponent 0 y squared will give you x squared plus 2xy plus y squared, which I think we already knew. But this is an illustration of the fact that you don't want to use the most complicated tool in a simpler situation. It's like you shouldn't use the sine law or the cosine law in a right angle triangle, or you shouldn't use the quadratic formula to solve when you can solve by removing a common factor. Fine. Plenty of practice on the worksheet. And this is a skill that my calculus students end up using if they choose not to factor. But I'll tell them to factor first anyway, so good luck.